Hello students, good evening. So we are in the session 4 of the work energy power topic. So today, right, we are going to discuss about two important things. One is the concept of this potential energy, and we will also see the modified work energy theorem. So both these things we are going to cover today. Okay. So what is this potential energy? Because remember, in the discussion when we were talking about the types of forces, right, we said, for the conservative forces, we are going to associate them with the energy term which we call as potential energy. Even when we are discussing about the different types of energies also, we talked about it. So if you look at the nature of work done by the conservative force, what is the nature of work done by the conservative force? We talked about the property of the conservative forces, right? If you are moving from one place to other place, we are moving an object from one place to other place, we can take the object in path 1, or we can take in path 2, or we can take in path 3, or we can take in path 4. Any path you take, the work done by this conservative force will be what? It is going to remain the same. It will not be changing. It will be remaining the same. Which means here we are having a situation where the work done, right, is only going to depend upon what is the initial point and what is the final point. Correct? When we are saying it is independent of the path, means what? It is depending on where you are starting and where you are finally ending up. So if you look at the basic work energy theorem, what is the basic work energy theorem? The basic work energy theorem is work done by all the forces acting on the body is equal to change in the kinetic energy. Change in kinetic energy means what? Final kinetic energy minus initial kinetic energy. Now the thing is, since the work done by the conservative force is not depending on the path taken, it only depends upon the initial state and the final state. The idea is we can get out of this job of calculating the work done by the conservative force each and every time, because we don't need to calculate the work done by the conservative force each and every time, provided we are able to account for this or adjust this in terms of some energy form for the particle. Why? Because look at this carefully. If you are assigning one more energy for the particle, this is not a real energy, this is the assigned energy. So if you are assigning an energy for the particle which depends upon the state or the position, since the work done by the conservative force also depends on what is the initial state, what is the final state, right? In the work energy theorem, we can adjust the work done by the conservative forces by using a new energy term that we are going to assign for the particle. This is not a real energy that the particle is having. This is the assigned value of the energy. That is the reason why, remember in the discussion about the types of energy also, what we said, potential energy is not a real energy. Potential energy is not really possessed by the body. It is basically the interaction between the object and the conservative force. The work done by the conservative force, right, is adjusted in a energy term. That is what we are calling as the potential energy. How it is adjusted, we will see. Okay, so how it will get adjusted, we will talk about it. So when we look at the idea of potential energy, right, as I mentioned, what is the idea of the potential energy? It is to adjust the work done by the conservative forces. That is the main idea. It is to adjust the work done by the conservative forces in where we are adjusting in work energy theorem, because we don't need to calculate work done by these forces each and every time, because it is anyway depending on initial point and final point, right? So we can assign an energy term for the particle, and how we will assign, we will see it. So look at this. What is the original work energy theorem statement? Work done by all the force is equal to what? Change in kinetic energy. Now work done by all the forces means what? In this we will have conservative forces, we will also have non-conservative forces. So work done by the conservative forces plus work done by the non-conservative forces, this is equal to what? Change in kinetic energy. Let us keep it as what? Equation 1. Now when we are defining the potential energy for the whatever the conservative force, it may be a gravitational force, it may be a spring force, whatever the conservative force we take, for that we are going to define the potential energy. Then when we look at the particle, right, we will talk about kinetic energy of the particle, which will be depending on the virtue of motion, and potential energy, which will depend on the virtue of state or configuration. This is going to be linked to what? The corresponding conservative force. Kinetic energy is possessed by that single particle, but potential energy is due to what? The interaction between the particle and the respective conservative force. So remember, when we talked about the initial discussion about the work energy theorem, what is it that we did? Initially the particle will have kinetic energy, potential energy. This is the method we did, right? And now we will talk about only work done by the other forces other than conservative. Means what? They are called as what? Non-conservative. The final state is what? The particle will have a kinetic energy, it will also have a potential energy. Now use the energy balance concept here. What we will have? If you use the energy balance concept, means what we will have, just like the way we did in the case of the basic form of the work energy theorem, right? Look at this, what we will be having? Work done by the non-conservative forces, right, which means other than conservative, will be equal to what? Final energy state minus initial. So if you take the kinetic energy together, it will be what? Ke final minus Ke initial. Potential energy together, P final minus P initial. So look at it, what we have? Work done by the other non-conservative forces is equal to what? Ke final minus Ke initial means change in kinetic energy. P final minus P initial means change in potential energy. This is our equation 2. In fact, this is what we will be calling as the modified work energy theorem, because work done by the conservative forces, right, they are adjusted in the potential energy term. They are adjusted in the potential energy term. So this is what we will be calling as the modified work energy theorem. Okay, so this is what will be the modified work energy theorem. But here we are trying to understand how the potential energy will be defined in relation to the conservative forces. We are trying to understand, how the potential energy is defined in relation to the conservative forces. So here what we will do is equation 2, right, we have work done by the non-conservative forces. Just take the value, substitute in equation 1. If you substitute, what we will have? Work done by the conservative force plus change in kinetic energy plus change in potential energy, that is equal to what? Right hand side, what do we have? Change in kinetic energy, that will get cancelled. So work done by the conservative force is equal to what? If you take it to the right side, means it will become minus negative of change in potential energy. We can also write it like this. If you put the minus left side, what we'll have? Negative of work done by the conservative force is equal to what? Change in the potential energy. So this is how our potential energy term is going to be defined. How we will define the potential energy for any conservative force? Negative of work done by the conservative force, right, is equal to what? Change in the potential energy. Okay, so this is how we are defining the potential energy. So remember one thing, potential energy is not a real form of energy. This is assigned value. No particle on its own will possess potential energy. It is always what? Particle interacting with the conservative force. That is what is the reason for the potential energy. Okay, now just keep a note of this particular formula. We will keep using it quite often when we go to the subsequent discussion. But look at this equation 2. Equation 2 is also important for us. From now onwards, right, mostly we are going to use this one. What is it going to be called as? It is going to be called as what? The modified work energy theorem. Henceforth it will be called as what? The modified work energy theorem. Okay. Now we'll just start with one very basic question. Potential energy of a body in position A is minus 40 joules. Means we can use probably symbol U for representing potential energy. What is it? Minus 40 joules, like that they are saying. Work done by the conservative force in moving the body from A to B is what? Minus 10. So work done by the conservative force is what? Minus 10. Okay. Find potential energy of the body in the position B. Means if you say potential energy of the body in position B is UB, right? We have to find that. What is the relation we have? Remember, negative of work done by the conservative force is equal to what? Change in the respective potential energy. That is how potential energy is defined. So change in potential energy means what? Final value minus initial value. Okay. So negative of work done by the conservative force is equal to what? UB minus UA. What is the work done by the conservative force? Minus 10 joules, right? So it will go here. Minus of minus 10 is equal to what? UB. That is what we are trying to find here. Minus UA. Look at what is UA. This is minus 40. So minus of minus is what? Plus. Is equal to UB. This is what? Minus of minus is again plus. We are looking for UB, right? Let us bring the 40 to the left side. It will become negative. So what we'll have left side? 10 minus 40 will be there. Okay. That is our UB. What is 10 minus 40 means? Minus 30. Check it up, guys. What must be the answer you should get? The final potential energy of the body is how much? It is going to be minus 30 joules. So this is a straight question based on the definition of the potential energy. This is the question based on the definition of the potential energy. So remember, how are we defining the potential energy here? It will be what? The negative of work done by the conservative force is equal to change in potential energy. This is the important relation that we keep using. Okay, guys. So you'll have to tell me whether you're able to get the answer or not. This is a straight question. Okay. So here the important thing is to look at the way we define the potential energy. Okay. Now we'll go into the modified work energy theorem, that particular relation. Already we have noted it down, but we'll just look at it separately. So what is it? Work done by the forces other than the conservative forces, means it will be non-conservative forces and any external forces, everything other than the conservative. Okay. The work done by all those other forces is equal to what? Change in kinetic energy plus change in potential energy. This is what is the modified work energy theorem. It is coming basically from where? The original form. We just adjusted the work done by the conservative forces by using a new energy term called as what? Potential energy. That's it. Now here, what we need to keep in mind is change in potential energy means if there is a gravitational force acting, we will talk about gravitational potential energy. If there is a spring force acting, we will talk about the spring potential energy. If there is an electrostatic force acting, we will also talk about the potential energy of this electrostatic force. We will call it as what? Electrostatic potential energy. Means kinetic energy means only one thing, but potential energy we can have many depending upon what are the given conservative forces acting in that particular case. Okay. So this is how we will use the modified work energy theorem, and we will see, because once we complete discussion about the potential energy, right, we are going to work out problems based on the modified work energy theorem. Mostly in JEE, mains and even advanced level, right, we will get questions based on the applications of this modified work energy theorem, like how we are going to apply this modified work energy theorem. Mostly in JEE advanced, we may not have like straight question based on the work energy theorem, but we'll have like questions where we'll use both these principles of mechanics. So principles of mechanics means, I think I would have told you that the conservation of momentum principle or the momentum based study and the work energy theorem. These two are called as what? The principles of mechanics. So mostly we'll have the questions where they will try to involve both these concepts. Okay, so we'll see when we solve some questions on that level, we'll be able to understand. Okay, so this is about the modified work energy theorem. Okay, now we talked about the idea of potential energy for the conservative force, but we need to see how the potential energy expression looks like, right? Because kinetic energy means we already know what is the kinetic energy of a moving particle, half mv square. That formula we have. But how the potential energy term will look like? So for that, right, the two conservative forces that we will deal with mostly in mechanics are what? The gravitational potential energy. Here gravitational means we look at only what? The simplified form. We will look at the simplified form. Okay, so we will see how the gravitational potential energy expression looks like. For that, what we will do is we will begin with a very simple derivation. Starting from the surface of the earth, right, we will take an object of mass m to a height h. So from point 1 we are taking up to point 2. Where is point 1? On the surface. Point 2 is at a height h. Okay, now while we are moving the object, gravitational force acting on the body will be downwards. Gravitational force acting on the body will be down. Why? Because gravity is always downwards, right? Now the work done by the gravitational force, when you are moving it, what is the work done by the gravitational force? The displacement is up, force is down. What is the angle between them? 180, right? So what is the work done? Force into displacement into cos 180. What is cos 180? Minus 1. So what is it? Minus mgh. Remember, we have already done this before. Work done by the gravitational force when an object is taken up, negative. When the object is coming down, work done by the gravity will be positive. Already we discussed about it. Okay, but here we are doing it to derive the potential energy formula. Now, how the potential energy is related to work done by the conservative force? Negative of work done by the conservative force is equal to change in the potential energy. Means final potential energy value minus initial. That is the relation between the potential energy and the work done by the conservative force. So look at this, minus of what is the work done by gravity here? Minus mgh is equal to what? P final. Final state is what? Height h. Minus P initial means what? Potential energy on the surface. Okay, so left hand side, what do we have? Minus of minus is what? Look at the left hand side, what do we have? Minus of minus means it becomes plus. LHS, what do we have? Minus of minus means it becomes plus, right? So LHS, what we are having? Plus mgh. So LHS is what? mgh is equal to potential energy of the body at a height h minus potential energy of the body on the surface. So one thing we need to keep in mind, the formula we have, right, for the potential energy, what is it? Negative of work done by the conservative force is equal to what? Change in potential energy, right? So that formula will always give us only the change in potential energy. That formula always gives us what? Change in potential energy. It will never give us what is the potential energy value at a location or a particular state. Okay, that problem is there in the basic definition. That problem is there in the way in which we are defining the potential energy concept itself. So what we will do in case of the potential energy is we will define something called as a reference state, where generally we will have the potential energy to be taken as 0 in the reference state. So what is the reference state will change from the case to case. Like in case of the gravitation, we may use something as a reference. When it comes to spring force, we may use something else as the reference state. So for this simplified gravitational potential energy, right, we will take the surface of the earth as the reference, where we will assign the potential energy as what? 0. We'll take the surface of the earth potential energy as what? 0, which means this we are going to take it as 0. If you take the potential energy on the surface of the earth is 0, that is our reference state. That is our reference state. Okay. Then look at this. What do you have now? This is becoming 0 means potential energy at a height h is equal to what? mgh. This is the usual formula that we'll keep. Potential energy of the body when it is taken to a height h above the surface of earth is what? mgh. From the surface, if you go into the earth, means you are going to the depth. Then in the same potential energy formula, normally if you take the object from the surface to a height means h will be taken positive. But instead of coming up, you are going into the surface of the earth. Then in that case, formula will be same, but h we have to take as negative. But h we have to take it as what? Negative. So from this formula, right, what is the thing that we will be able to understand as the height of the object above the surface of the earth is increasing? As the height is increasing, right, what is going to happen? Potential energy value will be increasing, because look at the formula, potential energy is what? mgh, right? H is increasing means potential energy also will be increasing. H is decreasing means potential energy will be what? Decreasing, like that. Okay. Now when we are dealing with the objects, right, we will generally consider the object as what? Point mass. But sometimes what we can have is the extended objects. What do you mean by extended object? Like you take a rope, okay, or you take a block, or you take a sphere, anything which is having some volume, that is what we call as what? Extended object. Now in case of extended object, look at it. No, if you take a block at some height above the surface, here you see block is not like a single particle, it is having lot of particles in it. The height of various particles will not be same, they will be different. In this case, how do we use the gravitational potential? Because in the gravitational potential energy we are simply saying what? It is mgh. So what is the h that we are going to use? In case of the extended body, what is the h value we are going to use? Okay, here, right, for now we will go with a simple case of the extended body, that is the symmetric bodies. Okay, for irregular shapes we will discuss it later, but here we will talk about what? For the symmetric ones, like a block is a symmetric, sphere is a symmetric. Most of the things that we see are what? Symmetric only, right? For the symmetric bodies, the h will be the height of the geometric center. H is what? For the symmetric body we will have the geometric center, right? Why it is so, we will understand about it once we go to the system of particles concept. For now we will just take it like a result. What is it? The h value we have to take it as what? The height of that for the symmetric objects only. For the symmetric object we are discussing here. Symmetric object means h value will be taken as what? The height of the geometric center above the surface. Okay, because extended body means you will have a lot of particles which are making the body, right? There h means what? We have to always consider the height of the geometric center above the surface. This is for what? Symmetric. Again I am saying, for the irregular ones we are going to see later. Okay, so that is what we will discuss in the system of particles. But here we are mostly going to deal with what? Symmetric objects. That is the reason why we are using this as a result. Okay, so this is how we are going to get the gravitational potential energy. Okay, and this is, as I said, the simplified form. When we go to gravitation chapter, right, there we are going to talk about what is the original formula for the gravitational force between two masses. So this is what the simplified formula for the gravitational force acting on an object due to the earth. In gravitation chapter we will see what is the original formula for the gravitational potential energy. Okay, so there we will again derive what is the potential energy value by using the original form of the gravitational force. Okay, look at this question. So this question actually helps us in understanding the concept of how do we measure the potential energy of the extended bodies. Look at this, a chain C of mass m and length L. is held in the position touching the ground as shown. Means what? The tip of that chain is touching the ground. If it is falling onto the ground fully, means it is fully falling onto the ground. What is the change in its gravitational potential energy? So here, look at this now. The chain is what? It is like a symmetric object. So where will be its geometric center? Midpoint only, right? So look at it. The geometric center is at how much height above the surface of the earth? It is at a height of L by 2. So initial potential energy, what is it? The geometric center is at height of L by 2, right? So what we will have? Mg into L by 2. Final potential energy is what? Because the entire chain is falling onto the surface, right? Means chain including its geometric center, everything is on surface. So final potential energy will be what? 0. They are asking what is the change in the gravitational potential energy. Change means what? Delta. What is it? Final value minus initial. So what we will get? Minus mg into L by 2. So that is what is the change in the gravitational potential energy. Check it, guys, whether you are getting the same answer or not. What will be the change in the gravitational potential energy? It will be what? Minus mg into L by 2. Okay. So we are done with the simplified form of the gravitational potential energy. Now we will go to the next one. What is the next one? Spring. For a spring, right, we will talk about one important property of the spring. What is it called as? Stiffness constant or spring constant. Generally, we will represent this with the symbol K, right? So look at this. We have a spring which is in the natural state. Okay. So from here, we will start elongating the spring. Elongating means what? We will start pulling it on one side. Okay. So from this is the point 0 where the elongation is 0. From here we are starting to pull. Okay. So we are pulling the spring to the right side, elongating it. By this time, what is the elongation value? X. When the elongation is x, right, the spring will start exerting restoring force. Spring force means what? Restoring force only, right? So if you are elongating to the right side, means restoring force will be acting to the left side, opposite direction. So you are elongating means spring will try to pull us back. So the spring force will be in opposite direction to the way we are elongating it. Now the thing is, spring force is not a constant force, it is a variable force. What is spring force? It is a variable force. Okay. So if you want to find out the work done by variable force, remember we cannot do simply F dot S, because that F dot S is only for what? The constant forces. Here it is a variable force. So what we will do is, from here we will take a small displacement x. We are further elongating the spring by value x, dx. This is what? The small increase in the length of the spring. We are giving a further increase dx, that is to the right side. Spring force will be acting to the left. So in this right, the small work done by the spring force is what? It will be kx into dx. This is the force, this is the displacement. What is the angle between them? 180, because displacement is to the right, spring force is to the left. So cos 180 means what? -1. So look at this, minus kx dx. This is a small work done by the spring force. Now we will elongate the spring from its original natural state. This is the initial, to a final state where the elongation is capital X. Final state, what is elongation? Capital X. So in doing this, we will try to see what is the work done by the spring. What we have to do? We have to integrate this expression from where? The x value, variable value will change from what? 0 to capital X. Initially, no elongation, 0. By the time we reach the final state, what is the elongation value? Capital X. By the time we reach the final state, what is the elongation value? Capital X. Okay. So now we are going to find out what is the work done by the spring force. Let us see what will be the work done by the spring force. So we'll just have to conclude the integration. From here, what we need to do, we have to conclude the integration. Okay. So look at this. Work done by the spring force is equal to what? This minus k will come out. Integral 0 to capital X, x dx. What is integral x dx means? X square by 2. Limits are there. Means minus k into capital X square by 2 minus 0 square by 2. Final limit value minus initial limit value. 0 square means what? 0 only, right? So work done by the spring, this is an important result, will be equal to what? Minus half kx square. This is what? Work done by the spring. So when you are elongating the spring by a value x from the natural state. From the natural state means what? The original length of the spring. If you just leave it like that, that is what we call as the natural state. From there we are elongating the spring by a value capital X. Then what is the work done by the spring in doing this? It will be minus half kx square. Okay, so this value we can just remember it. Then we are here trying to find what is the spring potential energy, right? Of course we are able to get the expression for the work done by the spring force, but what is our main objective? We are trying to find what is the spring potential energy. So what is the relation? Negative of work done by the spring force is equal to what? Change in the spring potential energy. That is how we define for every potential energy, right? Means what? Minus of minus half kx square is equal to what? Change in potential energy means what? Potential energy final, where the spring is elongated by value x, minus potential energy initial. Initial means what? The natural length. Okay, so minus minus becomes what? Plus. So look at it, what we'll have? Half kx square is equal to what? Potential energy of the spring when the elongation is x minus potential energy of the spring in the natural state. So here remember, in the case of the gravitation also we said the same thing. Potential energy, the way we define, it will never give us what is the actual potential energy at a location. We always have to use a reference. So here what is the reference we are going to use? We will use the natural state as the reference. What is the reference we are going to use in the case of the spring? Natural state will be taken as what? Reference. So in the natural state, we will consider the potential energy of the spring to be what? 0. Remember, in case of the gravitational force, simplified one, we have taken the surface of the earth as the reference. So we have assumed what? The gravitational potential energy on the surface of the earth is 0. Here what is the thing that we are taking as the reference? The natural state of the spring we are taking as reference. So this we are taking as 0. Means what we'll have? The potential energy of the spring when it is elongated by a value x, what is it? Half kx square. So when the spring is elongated by a value x means what is the potential energy value of the spring? It is what? Half k into x square. So here we can see that the potential energy value will depend upon the property of the spring, which is the spring constant, and also it depends on the amount of elongation. Amount of elongation means what? From natural length, how much we have elongated. Now the spring can also, like we have the natural state, right? So this is the natural state. So previously what we did, we have elongated. A spring can also be compressed. We have elongated, but the spring can also be what? Compressed. Look at this. If the spring is compressed by a value x, here we are not going to do the derivation because the derivation will be almost repeat. If the spring is compressed by a value x, then also the potential energy will be half kx square. Means whether the spring is elongated by a value x or compressed by a value x, the potential energy stored in the spring will be what? Half kx square. The value will be same. Okay. So this is about the potential energy of the spring. Maybe you can just later try and prove how in the case of the compression case also the potential energy of the spring becomes what? Half kx square. You can try to prove it. Okay. But as I said, here what you will do, you will start moving the spring to the left, then restoring force will be to the right, same will come. So here also what is going to happen, angle between the spring force and the displacement is 180. You will get say almost same result. Okay, so whether the spring is elongated or compressed, the spring is going to have potential energy. What is the potential energy value? Half k into x square, where x is what? In case of elongation, it is the amount of elongation. In case of compression, it is the amount of compression. Remember, x value will be always measured from the where? From the natural length. X value will be always measured from the natural length. Okay. So here sometimes, right, we have to be a little bit careful while looking at some questions. So look at this one. So these are the kind of questions where after knowing everything, right, we might just get something wrong in the basics. Look at this. A spring has a stiffness constant 4 Newton per meter and already elongated by 2 meters from the natural length. The spring is not in the natural length. Spring is already elongated. Okay. What is the work to be done in stretching it to 3 meters from the natural length? Means what? Here we have to look at what is the initial spring energy. What is the initial spring energy? Half into k is what? 4 into already initial elongation was 2 meter, right? So 2 square will come. Everything is the SI system of unit. So energy will be coming in terms of joules. Okay. So here look at this. What is it? 2 ones are 2 twos are. 2 into 2 square is what? 8 joules. That is the initial spring energy. What is the final spring energy? Finally, we are looking at what? 3 meters stretching has happened from the natural length. Means final energy is what? Half into 4 into 3 square will come. 2 ones are 2 twos are. 2 into 9 is what? 18 joules. So initial energy is what for the spring? 8. Final energy is what? 18. They are asking what is the work to be done in stretching this. So initially it is 2 meter stretching. Finally it has been stretched up to 3 meters from the natural length. So this we have to do the work, right? To stretch it we have to do the work. What is the work to be done? Remember, from the modified work energy theorem, work to be done is what? Change in kinetic energy plus change in potential energy, right? Work done by the external force or the other force is equal to what? Change in kinetic energy plus change in potential energy. Here the spring we are elongating it and then holding it, which means kinetic energy will be zero in both the cases. It is not like the spring is moving or anything. So we are initially it is elongated by 2 meters. Then we are stretching it up to 3 meters and then holding it. So there is no concept of kinetic energy here. That will not come. So work done will be what? Change in potential energy. Change in potential energy means what? Final potential energy 18 joules minus initial 8 joules. What is it? 10 joules will come. Check it guys. What is the work to be done in stretching the spring? It will be what? Final energy 18 minus initial energy is what? 8. That will be 10 joules. Okay. Now we have seen in case of the gravitational force and spring force, what is the relation between the work done by the respective forces and the potential energy term. But here we look at what is the general relationship between a conservative force and the respective potential energy term. So look at this. What is the work done by the conservative force? Means if the conservative force is F for a small displacement dr, the work done is what? F dot dr. If you integrate it from the initial point to final point, that will give us what is the overall work done by the conservative force. Why we are taking this? Because we don't know whether the force is going to be a constant value or a variable value. That's why we are going with this general result. What is it? Work done by the conservative force is equal to what? Integration F dot dr. Now what is the relation between the work done by the conservative force and the potential energy? Minus work done by the conservative force is equal to what? Change in the potential energy. Like say it will be what? Final potential energy minus initial. So minus what is the work done by the conservative force? Integral A to B. A is the initial, B is the final. F dot dr, that is equal to what? U final minus U initial. This is how we look at the general relation. Okay, so this will give us what? The general relation between the conservative force and the potential energy term. So in fact, if you look at it, right, this is in which form? It is in the integral form. So we also have one more form which we call as generally the differential form. The differential form is nothing but the form that we will have before integrating it. So look at this, as we said, right, for the small displacement dr, what is the small work done by the conservative force? dw, that is what? F dot dr. Minus dw will be equal to what? Small change in the potential energy, that is du. Always we will represent with the differential element d. So what we will have? dw is what? F dot dr, right? So minus F dot dr is equal to what? du. So this is what we call as the differential form. The one that you are seeing on the left side is what? Integral form. We have integrated it. The one that you have on the right side is what? The differential form. That is before integration. This one is what? Before the integration. Okay. Now here, right, we will also discuss about one special case. The special case is if the conservative force and displacement or the motion of the body are in the same direction. If the conservative force and the motion of the body are in the same direction. So look at it. If you have the force and the displacement dr, both are in the same direction. In that case, what will happen to this? Look at this. So F dot dr means what? It will be F into dr into cos 0. That will be du. Cos 0 is what? 1, right? So minus F dr is equal to du. From here we will have what? F is equal to minus du by dr. This will be only when we have force and displacement happening in the same direction. Remember, like this, most of the examples we talked, if there is a force which is trying to move a body from the rest, then whatever the motion of the body, right, will be along the direction of the force. Like, we have a force acting along the x-axis. Imagine we have a force acting along the x-axis. Okay, so which means what? The force is along the x-axis and displacement also will be along the x-axis. So in this case, what we'll have? The force will be equal to what? Minus du by dx. Here the displacement is happening only along the x-axis. Like that we can have. Okay, so this is what? It's a special case. It's a special case when the force and displacement are in same direction. Okay, So this result you just make a note of it, because this we will be using. So the special case where we have the force and the displacement same direction, then the F value will be equal to what? Minus du by dr. If it is along the x-axis, means what we can say? Minus du by dx. Now when we look at the potential energy importance, right, it talks about the state of the object, because potential energy is associated with what? State of the object, right? So potential energy will be linked to the state of the object. Now when we look at the state of the object, right, generally we'll be interested in knowing what are these equilibrium positions. So equilibrium position is, first we look at what do you mean by the equilibrium position. Equilibrium position means, equilibrium means what? Here we are talking about the translational equilibrium. Equilibrium means what? Balancing. What is balanced? Forces are balanced. Like look at this. This is like case A, case B, case C. Here this object is here, means forces are balanced. This is in equilibrium. Here also this is at rest, means forces are balanced, equilibrium. It's on a flat surface. This is also at rest, that is also in equilibrium. So when we see the three objects in equilibrium, right, we will see later that these three will represent three different types of equilibrium. All three are what? Equilibrium cases. But the three, right, they will represent three different types of equilibrium. So we'll see what are those. So in all the three cases we have the equilibrium. This is at rest, this is also at rest, this is also at rest. Equilibrium means what? Remember, so here if you look at the force here, force is what? We're talking about the conservative force, which is the gravitational force. Okay, it will be equal to what? Minus du by dr. Okay, that will be equal to what? 0. Here in this case what will happen? The force should be equal to what? 0. Then only we will talk about the equilibrium, right? So in this case what we see, net force will be 0 in all the three, case A, case B, case C. Net force will be 0. That is why we are calling them as what? Equilibrium. Okay, so equilibrium means what? Net force 0 means what do we have? The du by dr will be equal to what? 0. Du by dr term will be equal to what? 0. Okay, so which means in terms of the graphical representation, right, what we are going to have when we look at the graph of u versus r, the slope of the tangent that you draw for the u versus r graph. Remember, if you have anything like if you have a function y with respect to x, what is the dy by dx graphical significance? If you have the curve, slope of the tangent that you draw to the curve, that is what is the significance of dy by dx. So if du by dr is 0 means what? The slope to the graph, what is the graph we are talking about? U versus r, potential energy versus the position. That graph, right, will have its slope 0. So wherever you have equilibrium means the graph slope of the tangent will be what? 0. Okay, so this is about how do we identify the equilibrium. So whenever we talk about the equilibrium, right, for any type of equilibrium, whether it is the case A, so later we will see why we are calling the case A as the stable, case B we are calling it as what? Unstable, case C we are calling it as what? Neutral. Case A, what are we saying? It is stable. Case B, what you are saying? Unstable. Case C, we are saying it is what? Neutral. So why are we giving them these three names? We will try to understand it. But for all these three types of equilibrium, right, if you look at the equilibrium point, the slope of the potential energy versus position graph will be what? Slope of the tangent will be 0. And that means in terms of the functional relation, the du by dr value, will be what? 0. Du by dr value will be what? 0. Okay, so this is about how do we identify the equilibrium of an object. Now when you look at this case A, which we called as the stable equilibrium, right? You will see something interesting. If you try to just give some disturbance, either this side or this side, it will go to a position where the potential energy is higher. From the equilibrium stage, if you disturb it, it will go to a position where the potential energy is higher. Means what? The potential energy in the equilibrium position is the minimum as compared to neighboring points. Because of this, what happens? The object, when you displace it, means it will always have a tendency to come down to the stable equilibrium. So stable equilibrium, right, the object will always have a tendency to come back. If you disturb it, means it will always have a tendency to come back. Whereas in the unstable equilibrium, we will see why we are calling it as. If you just give some disturbance this side or this side, it will go to points where the potential energy is what? Lower. Remember, always in universe, right, everything wants to go from high energy to low energy, right? So what happens is, we will see that this ball will start just rolling down. Means if you give some disturbance, it will not come back. Okay, so it will have a tendency to move away. Okay, so here what is happening? There is a tendency to move away from the equilibrium. So here what do we have? We'll have a tendency for the object to move away from the equilibrium. So we will call this kind of equilibrium as what? Unstable. Because it is unstable, right? The moment you give some disturbance, means it will go out of the equilibrium. That is why we call it as what? Unstable. So why is it happening? Because the potential energy in the equilibrium position is maximum here. You can see as it is coming down, it will keep on decreasing. So in the equilibrium position, the potential energy is maximum as compared to the neighboring points. Okay. Then in case of the neutral equilibrium, right, if you give some disturbance to the left or to the right, it will go to a point where the potential energy is not changing. So here also potential energy is same. This side also potential energy will be what? Same. So it will neither have a tendency to move away, nor will have a tendency to come back. Okay, so this is what we call as the neutral equilibrium. Now in case of neutral equilibrium, potential energy will be remaining constant even when you displace it. In terms of the functional significance, right, whenever, so this is something that we will be discussing in basic mathematics also, like whenever a function has to attain a maximum value or minimum value. So here what is the function we are talking about? Potential energy function. If du by dr is 0, if du by dr is 0, right, that will be what? Indicating that the function can attain maximum value or minimum value. When the maximum will come? When the second derivative is negative, or we'll say less than 0, that is when maximum will come. See, maximum means what? The potential energy maximum means it represents what? Unstable equilibrium. When the second derivative is positive or more than 0, that represents what? The situation where the potential energy is minimum. That is the condition for the function to have minimum value. So that is what will be the stable equilibrium. What is a neutral equilibrium? You know, the second derivative also will be 0. Means we will not be able to conclude. The second derivative also will be 0. Why it happens? Because you know, you take potential energy like some number 20, constant value. That is what is neutral equilibrium. Potential energy everywhere is constant. Take it 20. What is du by dr? If you take a derivative of constant, 0. You take a second derivative, 0. So we will not be able to conclude. So for the neutral equilibrium, what is the condition? Everywhere the potential energy must be constant. That is why first derivative is 0, because derivative of a constant function is what? 0. Second derivative you take means that also will be 0. So this is the functional significance. How do we identify the maximum or the minimum of a particular function? Based on that, we can decide whether the equilibrium is actually a stable equilibrium or unstable equilibrium. Remember, in case of the stable equilibrium, the particle always will have a tendency to come back. Unstable, it will have a tendency to go away. Neutral, neither tendency to come back nor tendency to go away. Okay. Now we'll just try to look at this graph. This is a graph of the potential energy U versus position. Okay. Maybe you can just look at the graph and tell me. So here we are marking what? Point A, point B, point C, point D. You can tell me what these points will correspond to. Look at this point A. This is in a place where the potential energy is constant. So point A, we can say it is what? It is neutral equilibrium. Can we say or not? Point A will be what? Because there the potential energy is constant everywhere. That is why it is called as what? Neutral equilibrium. Point B, it is reaching a maximum. Same with point D also. Point B and D, they are corresponding to what? Potential energy maximum. Means what? That is, whenever the potential energy is maximum, that is what? That is unstable equilibrium. Correct or not? At point C, the potential energy is becoming what? Minimum. Means point C corresponds to what? Stable equilibrium. Point C corresponds to what? Stable equilibrium. Okay. So these are the kind of analysis we can do by looking at the graph. The other thing is, we should also be ready to do the analysis by using the equation. Like look at this. Now somebody is giving us this equation. They are saying that the potential energy of a conservative force is given by this function. U is equal to what? Ax square minus bx, like that they are giving a function where a and b are positive constants. Here a and b, both of them are what? More than 0. Find the equilibrium position. Means we have to find the equilibrium position and discuss whether the equilibrium is stable, unstable or neutral. Remember, first is what? So this function is in terms of the position x. So we'll take a derivative with respect to x. Take a derivative with respect to x. Derivative of ax square minus bx. What is it? Derivative of ax square minus the derivative of bx. What is derivative of ax square? 2ax. Derivative of bx is what? B. There is a minus. So this is a du by dx. Now remember, whenever we want to talk about the equilibrium, whether it is a stable equilibrium or unstable or neutral, what is the functional condition for that? The first derivative of the potential energy with respect to variable. Variable will be what? The position coordinate generally. That should be 0, right? Means 2ax minus b should be 0. So 2ax will be equal to b. X will be b by 2a. So that is the position. What is the position where we will have the du by dx 0? That is what? X is equal to b by 2a. That is the position where we will have what? The equilibrium. Now they are not just asking this, they are even asking what is the nature of the equilibrium. So we will be able to conclude that yes, equilibrium happens at x is equal to b by 2a. But they are asking us what is the nature of the equilibrium. Nature of the equilibrium means what? We have to look at what is the second derivative. Remember, what is the first derivative of the function? This is the first derivative value, right? What is the first derivative? 2ax minus b. Second derivative means what? We have to take a derivative of first derivative. Means we have to take a derivative of, what is this? Derivative of 2ax minus derivative of b. Derivative of b means what? Constant, right? 0. Here what is it? Derivative of 2ax means what? That is 2a. 2a will come out. Derivative of x is what? 1. So look at the second derivative. It is 2 times of a. Remember, already we know a is what? Positive. So second derivative clearly we'll see is what? More than 0. d square u by dx square is what? More than 0. Means what? When it is positive. Remember what we discussed? When it is positive, right? What is the nature of the equilibrium? It tells that, what is it? When it is positive means the potential energy function there is what? Minimum. When the second derivative is positive means what? Potential energy there is minimum. That means what? It corresponds to when the potential energy is minimum. So second derivative is positive means what? Remember the condition. First derivative is 0 and second derivative is what? It is coming positive. This represents what? The condition for the function to have a minimum value. This represents a condition for function to have a minimum value. When potential energy is minimum, right? When it is minimum means what are we talking about? We are talking about the stable equilibrium, correct or not? When potential energy is minimum, we are talking about the stable equilibrium. Okay, so this is how we'll have questions relating the potential energy to the nature of the equilibrium. Okay, so just try and practice this particular model of question, because I think in couple of times previous year mains also they have asked the question relating the potential energy to the nature of equilibrium. Just try and look some questions based on this model, and we'll continue our discussion in the next class.